Hi all. In this video, we are going to present a paper titled Focal Laws for Dense Object Detections. So we all know that deep learning based object detections falls into two categories. One is two-stage approach like RCMM, where the first stage involves generating candidate of object locations, and the second stage involves in classifying the object locations to which category it belongs to. There is another uh, types of deep learning based object detection called single stage detectors like YOLO or SSD, where it not necessarily to put a separate algorithm like selective search procedure for generating object locations. So, but however, despite it's being very fast in real time, but it couldn't be able to compete with the accuracy in comparison to the two-stage network like RCNN or fast RCNN. So the reason for that, uh, for it couldn't able to compete matching with that two stages, the reason is one of the reason is class imbalance. So we know that two stage single stage involves in a very exhaustive search like sliding window approach and generating around 100K locations, in which easily only few samples belongs to a particular category, other samples are not belongs to any category and belongs to easy examples. So this disparate in the ratio of positive samples and negative samples give makes the training inefficient. Uh, for example, these single stage algorithms put up a loss functions like cross entropy, where the dominant easy examples gives you a huge contributions and doesn't make the negative hard samples to contribute for the loss functions. So this paper tries to address that issues through modulating the cross entropy loss, introducing some scaling factor, and which those scaling factors can be decayed zero to the later stage, but initial stage it necessary to have a significant value so that it suppresses the easy examples and putting more effort on the hard examples. So this is what the main contributions about that. So once this modified version of the cost entropy loss has been set up, it has been applied to like a new neural network architecture called RetinaNet, similar to YALA or SSD, to try to validate this new training loss, which tries to address this imbalance between the positive samples and negative samples. So what this new entropy loss, so it's focused on the section 3. So we know that a standard cross entropy loss would be given by equations 1, and for putting up for setting up this equation 2, we can easily reformulate the equation 1 into these equations. So once this equation is there, if we see in the plotting for a different loss functions for different values of, for example, let us come to this one later. For example, we go to the figure 1. This is what unmodified version of the cross entropy loss, the blue one, where you see that significant portion of the well classified examples gives you a non-zero loss. So this has to be addressed by putting a special factor called modulating factor here, which if we are putting a very positive value, which decays and takes off the contributions from the well classified examples. So that's what it is illustrated in this part of this section 3. So what it does is this is what the introductions of the remodulated modified cross entropy loss. So this is a modulating factor. So for a well classified example, this would normally become misclass. It's almost nearly zero. So this modulating factor will be nearly equal to 1. For as PD tends to 0, this factor goes to 0. So for this setup, what it does is for well classified example, this makes to become 0, so that these contributions will be vanished for well classified examples. But if it is not well classified, then this almost, for example, if it's not classified, this pt is almost like zero point 0.9. This would be blown up 100 times, and this will it will have a significant loss functions, even though the hard functions are there. So this will be exaggerated in a for hard examples, and so that a small number of hard examples are well contributed in the total loss in compared to the large number of well classified examples. So that's a very simple idea here. And another, the equation 5 is another updated version of this equation. Usually this is what they does in a standardized version, putting like a balanced entropy where alpha can become between 0 to 1, where alpha is multiplied for classified one, and 1 minus alpha is multiplied for negative classified examples. So the same thing, updated versions should be given in the equation 5. So they put up this also for the reason that it gives more improved accuracy and greater numerical stability. So if you go to the, now if you are going to the example 1, for example, if the gamma is 0, this is going to be the standard 1. And if it is standard 1, you see the blue line is well above the x-axis, and this well classified example is going to give a heavy contribution to the loss, and it marks the very small number of negative samples here. But if the gamma values initially it increases to a very high value of point so like 5, then all the well classified examples are masked, and it focus on a very small number of positive hot samples like easy samples and hot samples. So once the initial training is completed, we can put a decay rate so that the 5 is slowly decreased to 2, 1, and 0.5 and 0, so that at later stage this well classified it cannot be a false positive or false negative, so that it will be like a true positive and true negative. So we can go into a traditional cross entropy loss, and where the training process can be well efficient, and it can goes to a true loss function like cross entropy loss. So this is the basic idea of this paper, and this can be put it into any single stage detector like SST or YOLO for efficient training, so that the accuracy can be so that the test time accuracy can be near to the two-stage process like RCNN or fast RCNN, or even it can be related to the not necessary to go for convolutional neural network based object detections like deformable part models and other algorithms. Hopefully we'll see you in some other video, possibly on mask RCNN in the next videos. Thank you.